Maxwell will be here in a few minutes, I believe. I was, well, I'll check the Discord for questions as usual. But if not, I thought it would be fun because I've wanted to do this for a long time. Oh, it's an Effect Solutions issue, not the Institute. Okay, yeah, I've got to take a look at that. So yes, so I want to implement Effect from scratch today. I want to, yes. Let me start again. Hello, good morning. Today I want to implement Effect from scratch. I want to do that. It's been on my backlog for a while. Hopefully Maxwell joins so I'm not talking to avoid and acting all funny and forgetting to speak. But yeah, if anyone has any other questions, though, feel free to plop them inside of the Office Hours channel. Or let me share a link to this. Office Hours begins. I think that link works. How deep are we going to go? Yeah, so I don't think incredibly deep. I'd like to start, basically sort of re-implementing a bit of the thunk video, though going less into about thunks, and then sort of extending a bit from there to actually make an effect type. Would be a good topic to also discuss why every simple result type ends up being a worse effect. Yeah. And I think that mainly has to do, well, there are a few orthogonal avenues of power that effect gives you. So yeah, let me just get started here. Let me know if this font is a weird size, too small or too big. It's a small font size, but I'm sharing a small window. So hopefully that balances itself out. So yeah, effect gives you many powers. It represents a computation. I'm not going to ignore the autocomplete. Gives us many powers. And this is why it's sort of difficult sometimes to explain what effect is in one sentence, because it sort of is a suite of things bundled up into one data type. One axis of power is this axis of laziness, which is what I kind of got into my video on thunks. So laziness, thunkfulness, or thunkiness. I don't know what's a more, I think I landed on calling it thunkiness, coining that. It sounds more fun than thunkfulness. Either way, it's all good times to make up words. So there's this aspect, which gives us, yes, deferred computation. I'll accept this. Suspended computation. Hello, Maxwell.
Hello.
Good morning. So I've decided to re-implement effect. 4 is taking too long to come out, so I'm going to do it myself right now.
Wow.
On stream.
This is crazy.
But yeah, and there weren't any other questions, so I was thinking of sort of doing this.
Let's do it. Why not?
It's something I've wanted to do for a while. I think it can be nice just to have out there as a reference. A very simplified regurgitation of effect. Probably not getting into asynchronicity, because that complicates everything. Not being stack safe, but just kind of talking about the underlying. I think just going through the A and the E and the R parameters in sort of a simple synchronous model. It could be a simple, helpful pedagogical simplification for people.
Sounds good to me.
Beautiful. Cool. So yeah, let me know if I go off track or people have questions, or you have questions, or you want to talk about anything else as well. Okay, E-N-R-N. Cool. So yeah, I was just sort of talking about, so Michael actually had a good interjection, which was that we should discuss why every simple result type ends up being a worse effect. So shade thrown at Dylan Mulroy's better result, which it could also be referred to as worse effect, two sides of the same coin.
Just republish it.
Yes, exactly. Alias it. I understand from a marketing angle, though. Better result sounds better. So, and then what else? I just want to make sure I'm not missing anything. There are some cases where effect.fn cannot be used, but effect.untraced.fn works. Okay, that's kind of a separate question. We'll get back to that one. I'm interested to see how the layer architecture is implemented because effect result error is easy to grasp. Yeah, I think we can get to a simplified version of the layer architecture, or at least to give you an idea. Yeah. When you look at the real code base, right, I think I've said this before here or elsewhere, which is if you looking at a real code base is nice and all, but if you really want to understand how a library works, try to build a simple version of it from scratch. And these days, you have a lot of help in that regard to build basically anything you want to understand in 100 lines or so of code. Probably will not be doing the generator stuff. I mean, maybe I can ask Claude to do the generator stuff, and we can take a look at that. But we'll see why that's kind of just a syntactic. That's some syntactic sugar, sort of. That turns it into a series of nested flat maps. So we'll look at sort of the lower level implementation. That's a little uglier to read, but has less indirection. It might be clearer to understand. So let's see. Effect gives us many powers. Yes. So there are these different orthogonal axes and this is why effect is sometimes difficult to describe because there's the power of laziness, thunkiness, deferred computation, suspended computation, what gives it sort of this workflow or blueprint structure. So many different sides of this ways of describing the same concept here, and that's sort of this is the computer science-y property that effect bestows upon us, but what are the actual user-facing benefits of this? This is what allows us to do things around computations, so before and after. So usually, if I've sort of went over this in the Thunk video, but if you have a promise, the problem with a promise is that this represents a computation. This is a sort of a handle. This is a handle on an already running computation. So we don't know how it began. It does not contain its own instructions for how to create this promise. It's something that was kicked off previously, and you're sort of handed this as sort of active grenade that the pin has been released from. And what this means is you cannot modify, once you have a promise, you cannot wrap a promise. You cannot enrich or decorate a promise to be a promise that it will first attach a log span, a trace span, and then run it and then remove the trace span. You can't retry it as well because you don't know how to kick off the promise. So it allows for aroundability. It allows also for sort of just sort of instrumentation, enrichment. What are some other decoration of computations? For instance, this is what allows for in terms of raw combinators, retry, repeat n, etc. Oh yeah, caching, timeouts. I guess you could write kind of a timeout on promises, but it would be funny, and you wouldn't really know when the promise was kicked off. But you can have like a maximum amount of time since you've been given the promise. Okay, thesaurus. Fair. So yeah, super useful axis of power, but that's just one thing. You could implement a version of promise that has this, and we will do that today. We'll probably start actually with this property. But then it still wouldn't be effect, because this does not imply asynchronicity. This could be all single-threaded and, well, JavaScript is single-threaded. This could all be synchronous. And it doesn't even have to be stack safe or anything like this, as our initial version won't be. So a very limited version of this. And then there's all the things of sort of error tracking at the type level. One could imagine a world where promise had an error parameter. So promise is an A. One could imagine an A and an E. That would be theoretically possible, and that would not imply laziness. If it kept all the other powers of promise, it could still track its error type. So that's if you get what I'm saying here, a sort of a separate orthogonal capacity of effect. And then there's the whole requirements tracking and dependency injection business. That the R parameter, and this is the E parameter. So you couldn't really enhance promise with the requirements tracking or the dependency injection, because that is also sort of that is dependent on laziness, I believe. You could probably do some other crazy things. But in terms of how effect works, and we'll see why this is very useful, because basically if we describe our entire computation, our entire program as a workflow, well, we get to choose where and when we run your whole application, which means we can set things up ahead of time, like creating a context map of all of your internal dependencies and sort of dropping that into your program and propagating it. So because everything is a workflow, this pure value that represents your program, the runtime gets to run each of these values, and it can make certain implicit states available to each running effect, because we know where and when it's going to run. We're in complete control over how these effects are run, as opposed to a promise, which kind of is going to be kicked off when it's defined. And so you don't really have that same amount of control. Okay, so these are just a few. Can you think of any other axes of power? Is that the right way to describe this?
The axes of power.
That sounds a little dark, actually. Maybe I shouldn't go with that.
No, I mean, I think this makes a lot of sense. I think the other piece that, like, the other, maybe two other axes that the laziness and like lack of function coloring and whatever that effect gives, include the ability to interrupt on a very granular level. Because with promises, you have to introduce another data type in order to be able to interrupt a promise. The abort controller is required. And it's not quite as granular of a control that you receive, like with an abort controller, that you have with effect. Like, to interrupt a promise, like, you just don't get as granular ability to interrupt computations with promise as you do with effect. I mean, you can do it, but you would need a separate abort controller for every promise. It just gets really annoying. And the other piece is the concurrency piece. So, like, and then Sebastian brings up a good point too. So concurrency and resource safety, I think, are the other two pieces that probably make sense to put in here. It's because having like the laziness capabilities of effect, like defining how concurrent computations are supposed to run, becomes really easy. And that kind of goes hand in hand with interruptibility. So like racing computations, you can do very granular racing as opposed to like promise.race, for example, which is very opaque in terms of like how things are going to be interrupted. And then, yeah, the resource safety piece, you would basically have to implement yourself in promised land. There is no, I mean, yes, there's the using keyword now, I guess. I don't know how well supported it is, but using doesn't propagate across scope boundaries. Like, it's kind of like Golang, if I understand it correctly. I've literally never used it, but I think if I understand correctly, using is similar to like Rust, not Golang, Rust, where when you exit the scope, you, like, that resource is dropped. Please, somebody correct me if I'm wrong. But with effect, you can like, the ability to control how resources are sort of like finalized or closed or like cleaned up, is again made explicit to you in the form of like a scope data type that you can attach resources to, and that allows you to propagate the lifetime of resources beyond the boundary of the current scope that you're operating within, which is really nice, and gives some very nice properties to like controlling resources in effect. So anyway, I think this is a pretty good list. We can probably like start doing some coding.
Yeah. Perfect. Yeah, let's see what the heck we're talking about. So I think we're going to start with just a very basic version that doesn't have resource safety or concurrency or interruptibility or any of the environment or error tracking, and just gives us sort of the very basic core of effect. And so let's make a new class, call it an effect. has some type parameters. We're just going to start with the A type parameter, which is basically means how this computation will succeed. So an effect of a number will succeed eventually with some kind of number. And let's make a constructor here, which will, okay, that's not so bad. I will call this instead, let's call it a thunk. So we have, or maybe I can call it run or something like this. I don't know what we prefer. Run sync, I guess I can call it, because that's kind of what this will be doing. I don't know if I want to name this some internal thing, but whatever. So really, an effect is, in the simplest pedagogical model, just a wrapper around a function, a nullary function that returns an A. And that really is what gives effect its blueprinty, thunky, suspension, workflow, etc., recipe capabilities. Oh yeah, recipe. Can keep adding synonyms. Because that's what a function gives you. That's the power of the function abstraction that we are already familiar with. We don't run it until we decide to run it. And then we can run it multiple times. So we can create functions that wrap other functions to decorate them or enhance them or enrich them. We could easily do that. Given an F, we can make a G, const G, that does some other things before calling F. So it does E and then H around it. And it can bundle this all up into a new function. So everything is sort of, we're building a larger recipe around smaller recipes. Some kind of thing. Void, whatever. This is really ugly. But we can do things before and after and maintain the blueprint, because a blueprint is really just a thunk, which is just a fancy word for a function of no arguments. But it's a function that gives, even if this were a function with arguments, it would still have this ability, this capacity of suspending the computation inside of a function. That's just how functions work. And effect is just the the lucky inheritor of such a capacity, and it makes the most use of this. And there's a reason why. Getting to what Michael said earlier, the reason why other effect imposters or other sort of well-designed abstractions that exist to satisfy a different quadrant of the trade-off space, like Dylan's better result, is
I think you mean worse
when
effect.
you do this, now that everything is in a function, you can't just use normal composition. You can't just use normal linear composition. We can't just call F and then call G and then call H. You can't use async await because async await is built for promises. Everything needs to be wrapped in other functions, which means in order to make this readable and usable and enjoyable at all, you need to sort of come up with your own special tricks or your own syntax for normal sequential composition. Which in effect's case would be effect.gen, which makes it, there's still some syntactic overhead here, admittedly, but it is pretty dang good and basically the best we can offer inside of TypeScript to have a readable sequential composition. But yeah, you basically have to redo everything. Sorry, Maxwell.
Don't forget your stars on your yield.
Yeah, come on, Zed. What the heck? And I don't even know what this is. Nonsense here. So do this, then do this, then do this. And we'll see what this turns into under the hood in just a moment, because we're not going to implement effect.gen initially. I guess it doesn't technically turn into anything else, but because this isn't a macro, but theoretically it'll turn into a chain of flat maps. It's morally equivalent to a chain of flat maps, and we'll see what that even means and why that's relevant. Some people like pipelines. That's totally fair too. I think though yep.
I was going to say, I think pipelines are really good. Like the way I usually, when I'm introducing effect to people or teaching it to people, like I recommend pipelines for composition. So like if I'm adding a retry or if I'm adding a timeout or if like I'm trying to compose higher order behavior onto an existing effect program, I think pipelines that's where they shine. I think pipelines are generally pretty terrible for business logic. That's where I lean into generators, because you don't have access. You have to like flatMap in weird ways to get access to the previous scope, or you need to use the like do simulation. It's like, why bother with all of that when you could just write a generator and get your like imperative syntax? I like
some
all the
people
people
just
that
love
are.
pipelines, and I agree with you, Maxwell. But hey, yeah, some people like really like Elixir. They like chaining things with this too. I also don't care for that as much.
I'm like less of a purist, I guess, than some other folks. But I listen. I don't want people to get me wrong. I am a pipeline enjoyer, but I think I'm also like more practical when it comes to like use the tool that makes sense for where you are in a particular like part of your code. Like if you're writing like a complex like piece of business logic, why would you ever use a pipeline? Like just use a generator. It makes it so much easier, and it's so much easier to read. And generally speaking, in my experience, the LLMs have a much better time understanding. They also like the higher order combinators in pipelines read better as well. So like, I don't know, my feeling has always been, in the way I've always taught effect to people, is use the tool that makes sense contextually, if that makes sense to folks. Yeah, pipeline enjoyer, not a pipeline diehard. Precisely.
Okay, cool. So let's keep going here, I guess. And maybe we just expose run sync. I'll think about this in a second. All right, so we have a way of the representing an effect here as a class with a constructor, but we haven't really seen what the heck this is going to look like in practice yet. So we have to sort of make an example here. What would we like to example program? Well, maybe we can have something like effect.succeed, right? How would we do this? Okay, 42. It always wants 42. Douglas Adams has ruined programming examples forever, but fine. It's good to have a nice default, I suppose. Okay, let's not have this private. Okay, so how would we get this to work? And then of course we would want to say sort of something like example run sync, and then we would be able to console.log this, and see 42. So, we'll make a new static method, a constructor. This is not how it works in effect exactly. It's a module, etc. But once again, this is going to be like the simplest way to give you a morally equivalent representation that can actually fit on a screen, and we can complete it in a day or in a session. So yeah. What have we done? So we made a constructor that takes a value. It's going to be generic. There's type parameter A, and that's whatever value we pass in is going to determine the output, the result, the success type of the returned effect. And in order to create an effect, well, we have to construct one. And we give it a thunk that returns an A. So really, we just wrap up. It's a bunch of wrapping. These functional data structures, these functional types end up just destructuring, doing something with the internal representation, and then bundling it back up into this nice higher level wrapper such that it can continue to be composed, and all the operations can be closed over this fancy new data type. So yeah, I hope that kind of makes sense. It's silly at this point. At this point, it's silly. And that's another problem with teaching effect, is that in the very basic, it's just like at the very basic level, we're just adding a whole bunch of ceremony, and it only starts to pay off when we need some of these capabilities, and we don't need one to just return and print the number 42. But hopefully we'll be able to quickly work our way towards something a little more interesting. And now let me figure out how to run this file. I think I added a task last time. Task spawn bun, run with bun. Yes, run with bun. Cool. And I think from now on I should be able to just hit a fancy keyboard shortcut. Yes. Okay. Cool. Maybe I'll just keep this really small over there, so I don't have to keep closing it. Great. And we're increasingly, I'm a little claustrophobic, but I like that. I'll take this. We could put this on the website. There are two kinds of effect developers: the ones that love it and the ones that still haven't faced the kinds of problems it solved. I think I agree with this. There are also some people, like, the DHHs of the world, who just love dynamic types, and God love them.
God love them.
God love them. Yes. Anyway, won't go off on tangents. I really did like Ruby on Rails back in the day. So much respect. But I eventually needed to come to types, and they were my home. Okay, so that's succeed, and this works because the run version of succeed, well, it's defining its own implementation here. So the implementation of run sync is whatever we put inside of this. So this defines how it's going to be run. It's just going to return the value that we give it. So that's great. And you can see here, obviously, there is the semantics of succeed are sort of implicit here. Like if I do something instead, like, math.random or math.random, and then I run this a couple of times, well, it's not going to be 42 anymore. I'll just run it. It's going to be the same random number each time, because if we see how this works, at this point, it's going to come up with the random number. It's going to stash it inside of our effect as a value. And then when we call its thunk function, well, it's just going to keep returning, giving us back that random value that was first created here, right? This is just the same as kind of random value, math.random, and then random value. Okay, so yeah, that's always going to be whatever it is every time we run it. Now, instead, we might want something else. This is where effect.sync comes in, where instead we get, and maybe I'll keep this around, and then do another one. I don't know. I might also just start commenting this out. I guess I'll delete stuff so it can all fit on one screen. We might want effect.sync, where each time we call it, we'll get a different random number. And for this to make sense, we need to make it lazy. And the way that we make it lazy is by wrapping it inside of a thunk, inside of a function. That's the only way to do it. And that's why the lazy constructors for effect take thunks. That's why you see thunks in various effect constructors. It's so that we can store off the computation and not execute it at the call site for various reasons. Okay, so now we need to make this constructor, which is going to look very similar, except we're going to wrap this value up in a thunk, if I can type correctly, and then we'll store off this thunk. So it's a thunk of A, and we don't need to wrap it anymore because it is the wrapper. So this is really like a pretty naked, thin abstraction over our run method. We're just storing off whatever implementation of our current effect is. Now when I run this, we're going to get different random numbers every time because it's stored off the entire computation, and we run that. So I hope that's pretty obvious. Great. And pretty soon we'll want to do other things like, log stuff, or maybe we could map over values. I think that's a really good one. So let's say we have this. This is called random. We'll keep this around. And how do I do code actions here? Add type annotation. Great. So this is an effect of a number. What if we wanted to have this be a random string or something? This is not a great example, but I want to change the type here. Or I could have is even. Maybe that's for the best. What if I wanted to be able to somehow work on the output of random and transform it? Well, that's where we might want to do something. And I'm not going to implement pipe, I guess, just yet. That'll be a bit of boilerplate. So let's do the version. All the pipeable effect combinators, methods, functions are dual. There's this function called dual. So you can pass in their operand as the first argument. And then the method. Sorry?
Sorry. I was going to say what you're doing.
Great. Yes. So first, they're multiple. If we had pipe, we could do something like dot pipe. I could ask Claude to add pipe for us, but whatever. And this is actually going to be map. So we'll stick with this. Obviously, this does not work yet. We have to implement map. So let's do this. Let's get map to work. And then we should be able to see that is even is going to be hopefully different each time. Probably will be. Actually, we're doing math.random. This is all a little weird. So maybe we'll think of something else. I don't entirely know. I'll multiply this by a large number, and then we'll see what happens.
You could math.floor and multiply it. Math.floor, the whole multiplication. This should work.
Yeah.
Should. Trademark. Should.
Let's see what happens. Cool. Maybe I'll print this out a few times just to make sure. What have I done? Okay, yeah. So we'll get different numbers, and sometimes they'll be random. So theoretically, once we get is even to compile, this whole thing should work. So we need to implement map now. So I'm going to steal the signature. Map is interesting because it'll have two data types, two input parameters. Actually, no, it won't. I'm sorry. Because this is not going to, well, there's different ways we can do it. I guess I do want to make this a static function. So we will need both an A and a B. I could have also made, effect explicitly does not have methods rooted on the data type, but so I won't even get into that. Never mind. Okay, so this is going to take some effect.
If you want to make it easier, we could just root it on the data structure, make it a method on effect.
Well, just I mean, this is basic. This isn't so much work, and it is technically how effect works. So
that's fine. That's fine.
I don't think it costs too much. So it might be a little clearer too. Just to have things done in the same way each time. So these are all going to be basically free functions that just happen to be, so we can have a similar syntax of being able to call effect dot whatever. But these are all sort of top level functions. They're all going to be statics here. So we're going to take some underlying effect as our first parameter, which is what we're passing in here, random. And then we need a function that will be given the output of that effect and then can return some other type. So what am I doing wrong? Input. Do I need to label this? I do. Cool. And it's going to give us back an effect of B. And then for this to work, we need to think about what to do. Well, we need to return a new effect. Always return a new effect. And then effect needs to contain a thunk. So that's sort of given. So we're getting closer. And then what we need to do is, well, we have ourselves an F. In here, we need to return a B. So can I say one as any, or one as B? Cool. So we need to return a B in here. So how do we get a B? And this is a fun sort of game of Tetris, type Tetris, that is really nice to play once you have a powerful type system where you don't even need to really think that hard. Obviously, these days you could just ask Claude Code, but it used to be fun back in the day to sort of just traverse type definitions and play with them. So and when back in the day when this was more relevant, it's nice to take an inventory of what you have. So we have ourselves an effective A. We have a function that goes from A to B, and our goal is to get a B. And so how do we get a B? Well, if we have a function from A to B, we can get a B as long as we have an A. But we don't just have an A, we have an effective A. So the question is, now we have a goal of here getting an A. So how do we get an A? Well, luckily, because we're inside of the effect implementation, and we're returning a new effect, we're wrapping everything up in a new thunk, it is actually safe in this context, and in this context only, to really run our effects. We wouldn't want to do this in userland code because once you run an effect synchronously, especially, or whatever, asynchronously, in any way, you sort of lose all of the compositional powers that you gain from effect. You're just running it there, and it's no longer a workflow or description. But as long as you're doing this inside of another combinator, you're building a new workflow out of smaller workflows, well, those capacities are going to be, those features, those properties are going to be maintained. So it is okay to run an effect here to get an A. So calling run sync on our underlying effect will get us an A, I believe. Boop. Yep, it's an A. And then we can simply return F of A. Great. And if I remove this wrapping effect and just return this, we would say, well, now we're returning an A, or a B, but we need to return an effective B. So that's why we're going to wrap the whole thing up in an effect, which makes this all safe and composable, etc. And I could inline this and say just effect.runSync and then return the mapping of that. I don't know which one's clearer to people. I guess I'll keep it as this for now. And now if I run our program, we should see false, true, true. And I can console.log in here to say A plus A. So when it was 727, we get false, 868 true, 195 false, which makes sense with regards to our definition here. Are there any questions with this? I mean, it should be, I hope, pretty simple, but if you've not, it's a lot of types. If you don't write a lot of type generic functions, that can just the boilerplate of that can be a little overwhelming or confusing, but we're just wrapping up.
Maybe we can take a quick pause and just say talk about how we don't have to get into it really, but maybe we can just talk about how this differs a little bit from like the actual implementation of effect. Like what is run sync actually in like the library? Like we have like I don't want to get too into it, but I like want to make it clear that like we're not just operating on thunks within the library. If it does offer like this is like the core of it, but when we construct an effect and then run said effect, what we get back is not a value directly. In the library, we get back a fiber, and we don't have to talk too much about fibers or anything like that. But if you can make an analogy between fiber and promise, I think that would be kind of like interesting.
Yeah, of course. So yeah, this is very much, we have not yet covered asynchronicity at all yet. This is very synchronous and not stack safe. Like if we keep nesting a bunch of maps together and try to run it, it might explode. If we do 200 chained maps or something. But in real effect, yes, when we run effects, we don't tend to just return. Well, you can call run promise, you can call it various number of abstractions, but sort of the core, various number of methods. But the sort of the root method that everything wraps is when you run an effect, you get back a fiber. And just as a promise, I said before, is a handle on an already running computation, a fiber, the analogy here, is that a fiber of a whatever e. This is a handle on an already running effect of a and e. So it's an effect that we've kicked off, and then we can it's nice to have for various reasons. Fiber has some other state that is useful in the running of effects, and we can then join them effectfully back into another effect and interrupt them, unlike promises. So it's nice to have a fiber. But yeah, that's kind of the difference, and that does entail a rewrite of this to a degree that it would be much less. It wouldn't fit on a screen, and it would be a lot more difficult to sort of understand the underlying idea. So this is a simplification, but one could, once we understand this, we could naturally evolve perhaps next week into exploring what a simplified version of an effect runtime would look like, because there is no real runtime here. It's just sort of this value that we're calling run, and it's responsible for calling run on its whatever effects it wraps, its child effects, and so on and so forth. Whereas in the actual implementation of effect, there is a runtime that sort of handles this for us, which makes it stack safe. It allows for asynchronicity and a whole bunch of other optimizations and nicety and features that we are not going to have in our very simple model here. Make sense? Oh, I'm not sure if you wanted to add anything else to that.
No, I think that, I just wanted to draw that comparison that like we're doing like something really simple here. We're just trying to get like the point across about like how the laziness properties of effect give you the ability to do some of this stuff. But within the library, to get some of the other benefits, the concurrency control, the interruption control, the like the dependency injection, et cetera, we actually have like a specialized runtime that is behind the scenes what's taking the effect program and interpreting it and running it and taking all of the different I'll call them instructions of your program, all of the different things that you want your program to do, and running each one. So yeah, definitely like this is good because we can get like a very clear understanding of what laziness gives us. But I wanted to make the point that like at some point looking at what the fiber runtime actually does under the hood, I think will be really interesting to folks too.
Thank you, Daniela, for correcting my brain fart here. Perfect. I think I was thinking of doing that. This always trips me up a little bit about TypeScript, that you can put returns in different places. I just wanted to make an effectful version of log in preparation for our subsequent examples. Will this be okay? Will this get angry at me if I make it really terse? No, thank goodness. Okay. So yeah, to get closer, to get a little closer to something real, it's nice to be able to map, to have one effect and then to change its value, but we can't yet perform other effects based on this. So I have to now here sort of run it and then log it. But what if instead I wanted to be able to, just run it and have it be logged? Well, in order to do that, we need to be able to get the value of is even out and then do something with this. Maybe I can call it, well, log here. And I guess I'll just make message take any, because that'll work. Can it even be multiple any's? Whatever. I'll do this. So, and this is where we want effect.flatMap. So effect.flatMap is very similar to map, except instead of just taking a pure function that does not return an effect, it takes an effectful function and will thread the result of this into this function, and then that function can be effectful, which it is here. So we'll get sort of our Boolean, and then we'll pipe that in there. Let's see what this will look like. I'll call this program, and let's try to implement this. So it's going to be actually incredibly similar to map. I'll duplicate this, except it has the word flat in front. And there's one other complication in that this can return an effect of B. But other than that, it's basically the same thing. So you can see where the term flat comes in here. There's going to be a second effect, and if we were naive about this, currently what this is returning is a doubly nested effect, which is no good, because f of a returns an effect of b, and now we've wrapped this whole thing in an effect of b. So that would be a bad time. And then we want to flat in this, and so our target here is just to get an effect of b. And so the semantics of this is we're going to first run effect of A, take its value, and pipe that into effect of B. And this whole thing should be lazy and wrapped up in a blueprint. So one thing you could imagine doing is just returning this effect wrapper, because that's what's causing that double nesting. And then, hey, look, it seems to type check. But this would be very bad. This would be very, very bad, because I don't know if it's terribly obvious yet, but if I do not run this program and run it now, and instead let's add a console log like we had a moment ago internally here, map A plus A, we're going to see that it actually executes eagerly, because this effect.runSync is not trapped behind a thunk. It is not suspended. We're doing it eagerly. So that's really bad. Every time we call runSync, and sort of this is just something that the maintainers of effect have to make sure they do, is to sort of maintain this invariant, maintain the laziness, the thunkiness in their implementations, and not run things too early, because flatMap is supposed to just construct a new blueprint and not eagerly run is even by constructing this, because this is also going to memoize its value. And if we later, well, actually, will that be true? I believe so, yeah. So now no matter how many times we call this, it's actually only executing map A once, and we're just going to keep getting the same value. So that's bad. We do not want to see that. So we need to indeed return, copy this, return a thunk, and then solve this nesting problem another way. And so what we have here is an effective B, but we just want a B. So how do we get that? Well, we can call runSync on it. As long as we do that inside of this returned effect, and then obviously return it, that's going to be okay, because that's going to be lazy. And that's indeed what we have to do. And I can collapse this into one line, but maybe giving these names makes it clear. So finally we get back our B, and we can just return our B. I will undo that last bit there, though. Okay, return. And now we see map A is called multiple times. Each time it is returned a new value, and it is logged. The logging is now part of the effect itself. We don't need to console.log after running the thing. I'll keep that there for later in case that is relevant. Does that make sense?
That tracks with us over here on my side of the screen.
You're starting to understand effect, Maxwell.
I'm getting there.
It's tricky. Okay, cool. Well, I mean, and this is kind of the core. It's even like at this point, there are other simplifications we can make. Like map doesn't need to be this whole thing. We can actually implement it in terms of flatMap effect and then succeed as well. It might be a little trickier than this. I might need to add some types. Return effect.flatMap. So yeah, map is kind of once you have succeed and sync and flatMap, you can implement a lot of other higher level things out of this, higher level methods. I will keep its own implementation because it's pretty easy to read. But yeah, now we can do things like all, for instance. We could do something like repeat. We can do. What are some other fun ones? What did I mention before? We can do aroundy things. Let me do one. Oh yeah, I know one that's fun. Is sort of timed. Timed is a favorite, which can return a new effect. Everything is going to return a new effect, and we'll just sort of let this work. So this is going to take an effect and then return an effect that returns a tuple of the value that effect returns, as well as a duration of how long it took to run that effect. And this is super easy as a consequence of being able to do things around the effect. We can trigger the effect here, trigger effect, and actually run it, which is safe because it's inside of a new thunk. So this is not going to happen until we actually run this new timed effect. But we can do things before we trigger. And then we can do other things after we trigger. So yeah, this is that instrumentability, aroundability feature that is, you just couldn't do this with promises. You could do this with promise, and you see methods like retry with promise, but these methods don't take promises themselves. They take, what is the magic word? It starts with a T. They take thunks of promises. So you might be able to sort of retry a promise, but you can't just pass in your promise. You have to give it a function that returns a promise. And it's hoping, of course, that is actually a function that sort of const make promise that will actually kick off the promise when you call that function, instead of having some pre-existing promise that you just happen to be wrapping up in a thunk here. That won't really make sense, and that will not actually work. So when you use promises, I'm not sure if if I've explained this correctly, but in order to retry, let's just say in order to do timed, it would need to be able to do something before the promise kicks off. So it could never just take a promise, because this means whenever you define a promise, it's kicked off implicitly. And so if this then takes, for whatever reason, 500 milliseconds, you're doing other things to before you call promise, timed with that promise, well, the result is going to be 500 milliseconds shorter than in actuality. Maybe it already completed, and it's going to say, oh, it did it immediately, but it actually took 500 milliseconds. So it would need to know that you've kicked off the promise inside of the call to timed. So it could do something very similar here, which means it needs to take a thunk of a promise. But if we do this, which would type check then, well, we still created the promise ahead of time. It's kicked off implicitly. We've waited 500 milliseconds, then we've tucked it into a thunk. But this isn't really the semantics that timed was expecting, where the thunk represents kicking off the actual underlying promise. We've just sort of referenced inside of our thunk a promise that was already kicked off. So there's so many ways to go wrong with promises, and where the type system will not even be able to save you. One might imagine, especially with retry, this is going to be a huge issue, because this will never succeed. If the initial promise fails and you're just sort of always referencing that initial promise, this does not rerun the promise. It's going to think it's going to call this thunk, and that thunk would be retrying the promise, but it's not. Really, really sad. Promises are evil. I need to convince people of this. Okay, so let's actually run timed, though it's not going to be very exciting here. But let's say effect.timed, and then we'll see what this says. And then I want to actually flatMap timed, which I can do actually flatMap log. And we can see why something like perhaps effect.gen would be nice to have, because now we're getting this increasingly nested, or even pipe would be nice to have. Maybe I'll ask AIs do it. Cool. And we get undefined and false. So that's weird. That's because I'm returning not is even, but I'm returning log. Let's not log internally. Let's just put the log on the outside. Cool. Now we have false and 0. Of course, that makes sense that it's false and 0. Cool. And then what else could we do here? Maybe a repeat method would be nice to have. Yes. And then we can sort of, maybe next time we'll have to get to A. But let's do it. Let's do a repeat. So, and then this will help time to make more sense because I could just give some ludicrously high number before repeating. So, repeat n. This is going to repeat the given effect a number of times. Effect A. It's also kind of fun to, maybe I could do replicate and then get an array of them, but replicate. Let's do replicate. That's more fun than just repeat. And this is going to get us an array of A. Uh-oh. Cool.
I think you're currently implementing repliacate.
Repliacate. Thank you very much. And I'm doing some various static members cannot reference type class parameters. Yes, I forgot to do the thing where it needs to accept the effect it's operating on. An effect of A. Great. And then not this.runSync, but effect.runSync. So yeah, pretty boring. We're going to have a for loop in here, and we're going to build a results array. And for however many times we've specified, we're going to call this effect and append it to an array. So before I do this, let's say const replicated is even, and then I can say effect.replicate 10. And then let's just see what replicated looks like. Yes. What's happening? Vim replicated. There we go. All right. So, and then of course I need to log it. I should have just done this. Not instead of timed, replicated.
Or repliacated.
Repliacated. True, false, false, true, true, false, 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 false. I believe it. So it's running our internal effect a whole bunch of times, each time anew, as we can see if I throw this. So however many times we specify. And so now, if I timed not is even, but replicated, it's still going to be 0, unless I make it some ludicrously high number. That took 1. That took 1 millisecond. At some point, it's just going to be too big. Okay, that took 10. You get the idea. It's going to have to be really big, and I probably blow some memory here. Okay, 620 milliseconds to do how many millions? 100 million. To run that 100 million times. Computers are fast. That's kind of cool. So yeah. So we get this really beautiful composable API. I might ask Claude or OpenCode or Codex or some agent here on the side, mysterious agent, to please add a pipe operator to our effect and rewrite our examples to use them. So that will be very nice to read. But JavaScript is slow. I mean, yeah, there's probably some, all the garbage we're generating. All these thunks we're littering all over the place. Cool, we'll see what happens there. But I hope it's clear. I mean, we've been an hour. We can go a little longer. Maybe next time we could do the error type. But I hope it's clear a little bit that under the hood, at least along one of these axes of power, it's pretty trivial, and it's really just all of this fun functionality falls out of... That's not enough piping.
I think it's probably just going to call pipe repeatedly.
Oh, there we go.
Oh, here we go.
There we go. There we go. Let's see what it's done. Cool. Check it out. Oh, of course. And then all of these need to be curried. Yeah. Otherwise, it'd be dual functions. Okay. Yeah. So now it rewrote all of our functions to take the effect they're operating on second. So there's reasons why I didn't do this originally. Maybe it would be easier to actually do yeah, this is where sort of the requirements of the real world make it more difficult to understand code. So maybe I will undo this and just go back to our simple examples. Even if it's uglier at the call site, it's going to be easier to understand, I believe, overall. So I will undo that. And maybe next time I can have it implement a generator instead. We'll see if that does anything interesting. Okay. Yeah, I don't know. Maybe that's a good stopping point. Are there any other concepts that are related to just this first, with what we have here, before we add a whole other parameter?
And also, we went for a while without answering or looking for questions. If there are any just questions that folks want us to answer.
Oh, there was one at the beginning that I said I would get back to that I think you might have an opinion on, which is from Philip or Philippe. Feel free to correct me. And there are some cases where effect.fn cannot be used, but effect.untracedfn works. I forgot when.
I think if Philip means effect.fn untraced, but without an example, it's kind of hard to say, but I'm assuming that Philip is talking about situations where you pass effect.fn or effect.fn untraced into a higher order function, like a function that expects to receive a function, like a map or flatMap or something like that. And I think that it works with function untraced because of because fn also supports receiving a name for the span as an argument followed by the actual function. So TypeScript just doesn't know how to resolve the overloads in the fn case, whereas with function untraced, there is no overload. It's just the function. It just takes the function. So in that case, it can actually infer. I bet you with fn, it would work if you typed the arguments, if you opened up and typed the arguments. But anyways, without an example, it's going to be really hard to answer that question more thoroughly.
Yeah, but in terms of, as long as you always define them sort of as some kind of const, my method effect.fn, that shouldn't ever be a problem, right? That would only be True. If you're trying to do it anonymously, I guess, is what you're saying?
Yeah, if you try to do it in tacitly within a flatMap or something like that, okay. And you want the arguments to infer. In this case, I'm not sure that it'll work because TypeScript may have trouble selecting which overload to use. But again, without examples, I don't know how to answer this question more thoroughly.
Cool.
Jay
it did actually implement gen. I don't know if we want to take a look at it. It seems to work, so that's kind of cool. And it doesn't seem to be much code at all in our example. Yeah, I mean, this
actually isn't too far off from how the original gen looked when it was first implemented.
Yeah, this doesn't obviously have to deal with the types of the errors or the R parameter, which adds some other complexity so that those infer correctly. This is going to be much simpler because it's only determined by the result value. And I'm not sure if this will infer correctly in every case. In this case, it seems to work. That is indeed an effective number. And if I change this to high, and it even added fn for us. Look at that. So now it's an effective string. That's hilarious. So yeah. Okay, that fn looks weirder. Oh, because it added logging and time tracking for us, which isn't exactly what it's doing. Oh, and fn is taking a generator. So instead of delegating to the underlying generator, it's done a whole bunch of craziness. But so that doesn't exactly help. Undo fn help. But yeah, gen is basically doing the same thing. It is going to. I mean, we'll need another lesson to discuss how generators work, because it's this function that returns something. It gets a generator. The generator calls next to get its next result type, which is a result of. Well, yeah, I don't actually know what it's done here. Maybe we could talk about this next time.
Yeah, I think actually for folks who are curious about generators, Harry Solovey has a really nice video that he did a while back on generators and actually how Effect makes use of them. Like, it's not exactly like what we do under the hood, but like it's a really good explainer on generator functions in general. And the differences, for example, between like yield versus yield star and all of those kind of like quirky semantics of generators. So if folks want to take a look, that's a good video to check out.
Cool. I mean, if you see generally, if you will, what's happening here is, well, first of all, notice it's lazy. So this is the function here is going to be a function that returns a generator. It's a generator function, if you will. That's kind of what the return type of a generator function is. Function star gets you a function that returns a generator. We wrap the whole thing in an effect, obviously, because we're converting it to an effect. So it's that same laziness blueprintness we're exploiting. We call the function to get this like a mutable generator iterator type thing. We try to get the next result, which is going to be some kind of sum type wrapper, enum wrapper of an effect. And then when it's not done, so does the generator yield more values? Basically, every time we call yield, that's going to correspond to generator gen.next returning this effect, and then this effect, and then this effect to us. And we need to make sure that we can give it back the result of that effect. That's kind of the contract here. So if we yielded an effect of where'd it go? Of a number, we need to, when we next call the generator.next, give it the result of that thing. So we can use it to call the next part of our generator function, which will then yield the log. So we call gen.next, assuming we're not done. Then the value of that next call was an effect of, it says any, because this is going to be multiple effects. So it was one of these effects. The first one will be that call to random. And then we run it. We get back that result, which is going to be a number. And then we call the next call to gen.next, passing in that number, which is basically like this part of it's like a way of cutting up a function into different runnable pieces. So the first time we call it, we don't pass it any arguments, and we get back this effect. Then we need to run that, which gets us the number. We pass it in. The number we passed in becomes n, or rather, this value becomes whatever the result of running the effect, which then gets bound to n. And then we run this up until here, and then the result of calling log with whatever that n is what's yielded next. And then we just keep looping, which is going to, then we're going to get that call to log, which we're going to run. Then we're going to pass its result, which is void, but whatever. It's discarded and it runs the next bit. And it keeps doing this until it gets to the end. And once it gets to the end, well, that means that's our return value. And that's the A. So that's that second type parameter here. And that's part of what is this special type here. It's either basically an effect of any or an A, and probably has some other, obviously, details on it, like whether or not it's done. So yeah, it just keeps running piece by piece our function until it gets to the end. And because it's all lazy, it's safe to do. Very fancy, very fancy. I understand it now. Thanks, types.
And for a bit of trivia, like some of the original implementations of Promise under the hood would compile down to generators. I don't think that's the case anymore, but it used to be that Promise was based on like generator syntax.
Very cool. Yeah, and reminds me of React Saga, perhaps. I don't remember React Saga. Or vaguely I do, because there's Saga is an overloaded term too, right? There's the RxJS Saga stuff, then there's distributed system Saga things for having compensation actions. I don't know. Which ones, do you remember React Saga, Maxwell?
I never used React Saga, but if I recall correctly, it leans very heavily into generators. Redux Saga.
I've said this a million times before as well, but the nice thing about effect.gen, because I've seen, you've seen people on the internet saying, oh God, to use effect, you have to understand generators, and it's crazy. I didn't understand how this worked until I just read it, and this might not even be our actual implementation. Our implementation might be different and more complicated. It doesn't matter. You don't need to understand that. You just need to understand the semantics of what this means at the program level, which is that it's basically like async await for effects. Just replace all the yields with awaits.
A question that sometimes comes up for folks who've never used generators before is, why do we need yield star instead of just yield keyword? And there's a semantic difference. This has nothing to do with effect. This is just generators in JavaScript. But when you're using a generator function in JavaScript, yield without the star indicates to the generator that you're yielding back a value to the generator that is not itself an iterable like a generator. But in effect's case, we use the yield star syntax, which indicates to the generator that, yes, this value is indeed a generator in and of itself. So anyways, there's like a slight semantic difference there.
Yeah, I wonder if it got it right in our implementation here. There would be some details, or if this would work even without that. I'm curious. What would happen at the type level? I'm curious if I just remove star here. Does it still all work? It might in our case, because we're not doing other things. It seems to work just the same. But I know that that's not always true. So
I'm going to link Harry, shamelessly plug for Harry. His
I don't
video,
think you could shamelessly. Well, I guess you can shamelessly, because there should be no shame. It's not you, unless you
shameless.
are Harry.
Unless you're Harry, I guess, yes. But I will plug Harry's video in the chat. I'll put it in my Twitch chat too. But it's a really nice 15-minute explainer on generators and how Effect uses them. And I when I watched it, I thought it was a really good like summary. So
Awesome. I will watch it as well. We could do a React video. Not like React the library, but like, the primary agent reacts.
Yeah, we need to start like reacting more. Like, we need to have faces that we make.
Oh, faces! It's too early to have faces. Whoa. I can't even do it.
Give Davide a thumbnail for the video.
Okay, cool. That was it. Good luck. We'll see what happens there. All right. Well, thanks for coming in, everybody. And we'll talk soon.
Cheers, everybody.